One of the things that's most important in this unit is to make sure that you have a solid understanding of the difference between thermal energy, heat, and temperature. All three are definitely connected together, which is why many people have confusions over what they are. The very first question asks you to review what the difference between heat and thermal energy is. Now, my question for you is, are you just rewriting what you did in your notes for the sake of writing the question, or do you actually understand the difference between heat and thermal energy? So you're just writing things down to finish the work, kind of, sort of? Okay, so without looking at your notes, can you tell me what heat is? Mm-hmm. Okay, so we've talked about three transfer processes for heat energy. What are those three heat transfer processes? Conduction, convection, and radiation. Okay, so write that down on the board. So heat is a transfer of ETH. So ETH is just an abbreviation for thermal energy. In order to use that definition, though, you have to be able to understand what thermal energy is. Okay. There's two parts to understanding thermal energy. What are those two parts? Do you remember your particle theory? Okay, so everything is made up of particles. So in order to have thermal energy, you have to have particles in your substance. Okay. When we talk about the number of particles, we're talking about mass. Okay. So if something is made up of a few particles, it has a low mass, versus if something is made up of many particles, you have a high mass. Now, you intuitively know this. You intuitively know this. So what I'm passing around here are different blocks. The blocks have the same volume. Okay. So, which one has the most particles in the block? How do you know? Can you actually zoom in and count and see the number of particles on that? So how do you know that? Heavier, so it's more dense. Okay. When we talk about how heavy something is, we're actually talking about the concept of a weight. Weight is very different than mass. When you talk about mass, mass is the number of particles something happens. What is weight dependent on? What is weight dependent on? Let me give you a hint. If you were to go to the moon, would you have the same weight? Gravity. No. You would have the same mass, but if you went to the moon, you would not have the same weight. Why? What is the difference between the Earth and the moon? Gravity. Yes. He was just reading your mind. Okay. So weight is a factor of gravity. reason why we say that the metallic block that you're holding there feels heavier is because there's more particles from which the force of gravity is going to pull down on. So in order to have thermal energy, you have to have particles. In order to have thermal energy, you have to have particles or mass. What is the other thing that we look at when we talk about thermal energy? One more thing. Yes. Absolutely. 2 days ago, we compared a coffee cup and then and the thermal energy in the coffee cup, versus an iceberg. You said that the iceberg had more thermal energy. How is that possible when things move a lot slower in something that's cold like an iceberg as opposed to something that's hot like a cup of coffee? Exactly. So you have to consider both the number of particles and how fast they are moving. When we talk about heat is the transfer of that thermal energy. So then what is temperature? What is temperature? No. Okay, so temperature is actually this. If you have a higher temperature, the particles are moving faster. If I have a thermometer, okay, and if I have particles that are in the alcohol part of that thermometer, how come the thermometer level goes up in a hotter substance? Yes. Okay, so the collision between the particles will make them spread out. Does that help a little bit with helping to clarify those two concepts? Particles don't cease to move until minus 273 degrees Celsius. So there's still actually movement at minus 40. Hello. So at minus 40, the particles still have movement, but definitely not as much movement as they would at plus 40. Other questions? This is one of the most important fundamental concepts of this unit. What are the questions that you have about this?
Particles don't go away, they just slow down when it gets colder. There is a point of absolute zero, like what is that? Or not absolute zero, as opposed to constant.
When something is a solid, the only type of movement the particles have is vibrational motion. So they stay at a fixed point, and it's like they're shaking. Yeah, exactly. Once you get into a liquid state, you have vibrational motion, but you also have rotational motion. And then when they start rotating, those particles start bumping up against something else. So liquids generally take up more space than the solid state. That doesn't work with water. Water is a special case. When you get to a gas, the particles have vibrational motion, rotational motion, and translational motion, which means they travel in straight lines until they collide with something, and then they ricochet, bounce off this, and they take up much more space. So you don't want to put a propane cylinder in a place that's going to get very, very hot. right? Because you have a compressed gas in that propane cylinder. It's actually a liquid when it's in the propane tank. If you heat up that propane tank too much, it's going to take up more space, more pressure, and that propane tank is going to become quite dangerous. It can explode.
My mom, when she's working nursing, she knocked off the top of an oxygen.
Oh my gosh, that is a dangerous one too. And oxygen is incredibly flammable. So if that would have created a spark, you would also have fire, not just loss of container integrity. Question, I've got to plug in my computer here. Question number 2, how can a hammer increase a nail's thermal energy when there is no transfer of heat? Okay, so what's going on when you hit the nail with the hammer? Movement of? Okay. Pardon me? So, remember, we're talking about thermal energy, which means we're either adding particles or we're somehow making the particles move faster. Sometimes it's both. So think about a nail. Here's the head of the nail here. Then you have You're traumatizing to draw pictures for. Thank you so much. There's a reason why I'm your science teacher and not your art teacher. Okay, remember those substances are made up of particles. When the hammer hits the nail, is the hammer transferring hammer particles to the nail? No. Okay. So then how is it possible that the hammer is causing the nail particles to move faster?
Because it's
Exactly. When it hits the nail, it's actually going to cause those particles to move faster because you have the kinetic energy of the hammer coming down on the nails. It doesn't mean you need to try to test it out on a person and see if you can make your hand warm by hitting her. I appreciate you wanting to make physical science more of an applied science, but yeah. Consider a coffee cup at 75 degrees and an igloo at 13 degrees. Which one has more thermal energy and why? Does the igloo, gentlemen, ladies, does the igloo or the coffee cup have more thermal energy and why? How many people say the igloo? How many people say the coffee cup?
over what?
It's the igloo. Do you need to go get a drink of water? Do you need to go get a drink of water? Or? Okay. It's definitely the igloo. Are the particles moving faster in the igloo? No. There's more of them. Because there is more of them, there's more thermal energy. Next question. Does a thermometer measure thermal energy?
Just get a question. Is that why skinny people are cold?
Say that again.
Is that why skinny people are cold?
Because there's more of them? No. No, it isn't.
How was that for your ears?
Oh, never a dull moment.
Hey, now that it's said, theoretically true.
Okay, going back to the question. Does a thermometer measure thermal energy?
No.
No, it only measures one part of thermal energy. The part of thermal energy that it measures is how fast those particles are moving. Okay. Measuring one part isn't the same as measuring the whole thing. Conversions. I'll write up the conversions on the board for you. So we start off with question 5A. With 100 Kelvin, we need to subtract minus 273.15. What value are you going to get? Is that your final answer? How many significant figures do you get?
5.
Oh, do you remember those lovely things?
5.
Nope.
5.
What's the rule about adding or subtracting? You only count the number of decimal places after. So you actually get 3 significant figures, no digits behind the decimal place. The correct answer is minus 173. B, we have 273 Kelvin minus 273.15 degrees Celsius over Kelvin. And that is going to give us 0 degrees Celsius. Again, we do not get any decimal places. Okay, I'll have to photocopy another one. I don't seem to have extra. Did somebody pick up Coleman's notes the other day? Because I thought I put some on his binder. Okay. 6A. You have to go from Celsius to Kelvin. So 100 Celsius plus 273.15 Kelvin over degrees Celsius. This is 373 Kelvin, no decimal places. B, you have minus 50 degrees Celsius plus 273.15 Kelvin. And that will give you 223 Kelvin. No decimal places because there are no decimals in the original equation. For question C, by definition, 0 degrees Celsius is equal to 273. No decimal place because there's no decimals in 0 degrees Celsius. Question for you. Do you want a formula worksheet? Or do you want to create your own formula worksheets? You want me to provide one? Okay, I'll do that then. Today, we're going to talk more about heat energy and how we can measure heat energy. I am hoping that tomorrow we will be able to do a lab looking at determining the amount of heat transfer that goes on between one of those blocks and water. Suppose we took the block, so one of those blocks that's out in the classroom right now. Let's say we heated that block to 100 degrees Celsius. And then we dropped that block into a container of water that is about 20 degrees Celsius. What is going to happen to the water?
It's going to drop temperature.
Why?
Because
Absolutely. So you know already that heat transfer will occur when something transfers energy from the warmer substance to the cooler substance.
Why is it when you take a water bottle out of the freezer and in that certain state where it's still liquid and you shake it, it turns ice immediately?
I think that's due to supercooling. I've seen that phenomenon before. I'll see if I can find a better explanation. I'll have to look and see if I can find a good definite or explanation for it, because off the top of my head, I'm not really sure what's going on. Okay. So when we transfer this block into the water, it is going to transfer heat to the water. What's going to happen to the water temperature? Okay, so the water temperature is going to increase. My question for you, how do you think we are going to figure out how much heat transfer occurred between the block and the water? Okay. So do you think there's a device in the lab that I can just stick in there and it's going to say 50 joules of energy of heat was transferred?
Probably magic.
Oh, I'm not going to make it that easy.
Is there really a thing that does that?
No.
Probably like going like.
No, there isn't.
It's like block heat, subtract water heat or something.
Oh, okay. That's interesting. So continue on, Jesse.
That's all I got.
That's how you got. Okay, that's how you got. Okay. What things do you think we're going to have to keep track of during this experiment? Pardon? Why?
Because if you have 20 degrees Celsius water, just a shot glass, or if you have 20 degrees Celsius and a 5-gallon pail, there's a lot more water to heat up that.
Okay. So volume of water absolutely is going to make a difference, because if you didn't hear what Coleman said all the way over there, he was saying that if you had a small glass of water versus a 5-gallon pail of water, you would have a lot more water particles in here if you have. So we need to know how much water there is. What else do you think we're going to need to know? Okay. So we've got a few blocks out there. Do you know what your block is made out of, Jesse?
Brass.
Yeah. Do you know what your block is going to be made out of? Okay. So if we have a block of brass and we have a block of wood, and brass goes into one container of water, the wood goes into a second container of water, do you think that the water is going to heat up by the same amount in both? Why do you think it does that? Okay, so density. Okay. So the type of substance we need to know something about. Already, without me doing very much theoretical work, you already know that that brass block is denser. There's more particles in it, which means it's probably going to influence how much heat can be transferred to the water. Absolutely. There is one more thing that I'm going to have to keep track of. I have to keep track of my temperature. Now, I can't measure the temperature of that block, because think about how we measure temperature with the thermometers, right? I can't put my thermometer in that solid block and measure the temperature.
Could you put it in an oven to put it at an exact temperature?
You could. What we do when we heat up the blocks tomorrow or Monday, whenever we do this lab, is we measure, like we put the block in boiling water, and we let it sit in the boiling water for about 5 minutes. We measure the boiling water temperature, and we assume that the block is equivalent to the boiling water temperature after sitting in there for a few minutes. Mm-hmm.
But not all the blocks will get the same temperature.
It could leave it in longer, but eventually the temperature should equalize. Ladies? Haley, Scott? Don't lose track of what we're talking about. But we do have to leave it in long enough that the temperatures will equalize. What we can keep track of is the water temperature. So if I know that starting temperature of water is 20 degrees Celsius, then I can measure how hot that water temperature becomes and figure out the difference. We need to know all three things. Now, this one, the type of substance, is really important. So on the front smartboard here, we have a graph. Okay, the red line represents pure metal. We have a red ball facing back, a red ball facing forward. We have a white front, and we have bubble wrap. And in all cases, we've measured plate temperature. What you should see from this graph is that there is not equal heating. Okay. And this is because they're made up of different things. You intuitively know this. Because if I ask you to do this, you would probably be able to tell me without doing it. Yeah. What do you notice? But it's in the same room. Oh, bigger, yes. What else? Heat rises, so maybe that has something to do with it. Why do you feel the sensation of coolness when you touch the leg of the table? Okay. Okay, so here's the table here. Here's okay, I'm going to stop drawing for you, because you're making me feel really, really positive here. Okay, think about this. We know that heat transfers from the warmer object to the cooler object. What is the warmer object, my hand or the table leg? My hand, because my hand is probably about 35 degrees Celsius and around there. Versus the table leg is going to be about 21, 22 degrees Celsius, because that's about the room temperature right now. Why does my hand feel cool? It's because the heat is moving away from my hand into the table leg. There's no such thing as coldness. Think about this. Why is a room dark when you first come into the school in the morning?
Because the lights are on. I really don't want to take it.
There's no light.
I just did. Oh, okay.
There's no light. If you want to make a room dark, you have to take away the light. Ask somebody who suffers from migraines. They can tell you exactly what needs to be done to a bright room. You're nodding your head rather emphatically. It's like, take a towel and staple a towel and don't let any light into that room. All right. So a good absorber takes in a lot of heat, but at the same time only increases temperature a little, and it holds it for a long time. And every substance has a unique ability to do this, and we call that ability specific heat capacity. I'm going to give you a few moments to write this down somewhere safely. Metals tend to have very low specific heat capacities, which means it does not take a whole lot of energy to change the temperature of those metals. Think about cooking utensils. If you decide to try to cook with a metal spoon and stir the soup pot and leave your spoon in the soup pot, what happens to that spoon? Very warm. It's probably going to be so hot that it will burn you the next time you try to stir the soup pot. Cooking utensils that we choose to work with are generally low conductors with high specific heat capacities. Take a look at water specific heat capacity. It is almost 100 times greater than that of iron, which means we have to put in a lot of heat energy to make the temperature of water go up. That's critical to you. You are, depending on if you're male or female, 68 to 75% water, which means if you get a fever, that water absorbs the heat and keeps your body cooler than if your body was made up of 75% vegetable oil. Females have a higher percentage of water than guys in their body. Guys tend to have more muscle mass. Oh, I knew that was going to happen. Yeah. Sorry, ladies, that's just biology. That's not discrimination. Okay. Yeah. If you have ever babysat an infant, yeah? Okay. If they don't want to drink a cup of water or eat something, can you force them?
Yes.
Really? I would like to see you force a 9-month-old to take a bottle of water. So when a small child has a prolonged fever, we get very concerned because it's hard to force small children to take in the water that they're losing because they have a high fever, or if they have diarrhea, maybe they're losing a lot of fluid because of the diarrhea or throwing up. So usually after the second or third day, parents are taking their smaller children to the hospital for fluids. At least with adults, we might not like drinking water, but we can force ourselves most times. But it is possible for you to lose far too much fluid when you're sick and you have to go for an IV to get some fluid. Okay, you have already guessed the 3 things we need to know about to do the calculation. But instead of a volume of water, we're going to use mass. And the reason why we're going to use mass is because when we're given specific heat capacity, we're given a standard unit that includes grams. So we need to choose a measurement that also has grams in it. You do not need to memorize the list of specific heat capacities. You have a table which will tell you the specific heat capacities of substances. If you take a look at the table that I've just given you, there are 2 pages. On the front side, we have different information for specific elements that we're going to be using. We're interested in the last column on that table, where it says specific heat capacity. If you take a look at the set of units that you have, it is joules over gram degrees Celsius, which is why our mass must be in grams and our temperature has to be in degrees Celsius. It needs to match what is given to you in your standard units. Depending on whether or not you're solving a chemistry problem or you're solving a physics problem, it is possible to have a table of joules per kilogram degrees Celsius. And this is because in physics we usually deal with very large amounts or very large things, versus in chemistry it's a lot smaller, so we measure the substance in grams. Just to let you know, there's two possible tables that you can see. There's other information here, but we're not going to use that for a little bit yet. On the second side of the page, there are specific heat capacities for the three different phases of water: ice, water, and gaseous water in the top three. Those are also popular questions. We will often be working with problems that use water. This is what the formula looks like. Q equals mc delta T. Q is heat energy. M is mass. C is specific heat capacity. Delta T is temperature change, which means final temperature minus initial temperature. This is important because we could have a temperature increase or a temperature decrease. Think about this example again. Let's say you put that brass block, which is at 100 degrees Celsius, into water that's at 20 degrees Celsius. You've already said that the water temperature is going to go up. Has heat been added or removed from the water? It's been added. So is that going to be a positive Q or a negative Q? It's going to be a positive Q. So positive Q means that heat has been absorbed versus a negative Q means that heat has been lost. For example, if we were able to take the temperature of the brass cube at the beginning and then measure the temperature of the brass cube at the end, we would see that the brass cube loses heat because its temperature goes down. However, we don't have the ability to actually measure the internal temperature of the brass to track that in the size lab. There are some substances that we can do. So last year, Keeley designed an experiment to track the temperature as a couple of substances melted. So she took test tubes of substances, and she actually froze the thermometer inside the test tube of substance, and she was actually to measure the temperature change of that substance even when it was in a solid state. So it is possible to do that. But you have to have the ability to melt that and then have a temperature that can withstand the heat and be embedded in that, which for brass is quite high. A couple 100 degrees Celsius. Okay. All right. Oh, what happened to my? Okay. I seem to have lost my questions. I'll give out this worksheet and we'll work through the questions on here together. There you go. All right. What you need to be able to do is pick out information from a STEM, which is a question, and then you need to determine something within this mathematical relationship. So it says, how much heat, which letter is representing heat? Q, M, C, delta T? Q is, that is our unknown. Is required to raise the temperature of 500.0 grams of liquid water. 500.0 grams is what? We've got three choices. Is it a mass, a specific heat capacity, or is it a change in temperature? It is a mass. Do not leave off the decimal zero. Don't cheat yourself. That decimal zero is significant. It says that the water has heated from 25 degrees Celsius to 80 degrees Celsius. This is the temperature change over here, which means I have to go final minus initial in order to figure out my temperature change. The final temperature is 80 degrees Celsius. The initial temperature is 25 degrees Celsius. What is the change? 55. There you go. But C is missing. I am not going to give you a question that has two unknown variables. That means C has to be available from somewhere. You're looking in the right place.
C is the object.
The specific heat capacity of what's the substance?
Water.
Okay, where are you going to find the specific heat capacity of liquid water? You've got it, Stefan, and 4.19 joules per gram degree Celsius. If you're not seeing where Stefan is looking at, you need to turn to that data table that I gave you. Water is on the back of that table. We want to look for the state of liquid water. And if we go over and read the specific heat capacity, it's 4.19. We will use this number a lot. You'll probably have it memorized by Tuesday or Wednesday of next week. That's how often we'll be using it. We are solving for Q. Q tells us that the mass, the specific heat capacity, and the temperature change of the substance are all important in figuring out how much heat has been transferred. You actually already identified that over here, except for, instead of saying volume of water, we're going to say mass of water. The reason why we're saying mass of water is because in our standard, it's in grams, not in milliliters. All right, let's do some substitution. We'll put in some numbers. Oh, just made it there. All right, do some number crunching, please. When you do this calculation, you are going to get a calculated answer of 115,225 joules. Whoops. Which has the wrong number of significant figures. This is a multiplication problem. What is the rule?
We can only have one.
Nope.
Well, 1 and 2 decimals.
Nope. The answer is 2 sig figs, yes, because in multiplication and division, we look at all the numbers in an equation. For example, here, 1, 2, 3, 4 sig figs, 1, 2, 3 sig figs, 1, 2 sig figs, which means we only get 2 significant figures. I could do this because these trailing zeros are not significant. What is the other thing that I could do? I could rewrite this in the form of scientific notation. Is this a lot of heat or a little bit of heat? Not sure. What about if you were supposed to be paid $115,000 for work? Would that be a lot of money or a little bit of money? Well, that'd be pretty sweet if that was your paycheck for a month. $116,000 or $120,000 in your bank account. Woo! Okay, so this is a lot of energy. Now, when we get to really big numbers like this, sometimes we convert from joules into kilojoules. Think about grams into kilograms or milliliters into liters. Do you remember how many milliliters go into a liter? All right, and if I had grams, how many grams would go into a kilogram? 1,000? Uh-huh. Now, I can take 1.2 times 10 to the exponent 5 joules and make that be, that's kilojoules. Remember that when you do a conversion factor, it's always what you need over what you have. There are 1,000 joules in 1 kilojoule. How many kilojoules is this? Okay, or 1.2 times 10 to the exponent 2. This is 1 times 10 exponent 3. So in a shortcut way, if I did this, what would be a short way for me to figure out what the new exponent should be on the scientific notation? You haven't done multiplication and division of stuff with exponents?
Yeah, you just subtract.
Yeah, subtract.
Are you retired? No,
Oh, she's so mean. She's making us do math outside of math class. No. I want to bring your attention to question number 4 on your worksheet, because in question number 4, you're told 1.9 kilojoules. However, in order to be able to plug this into the formula, you're going to have to convert 1.9 kilojoules into joules. Okay. What I want you to do for tomorrow is to try question number 3, please. I'll go through this conversion tomorrow, and then we'll finish this up. We might only get as far as the pre-lab for the lab and have to do the lab on Monday, because the lab on Monday takes a full class. Okay.